Good day, folks. Today we're going to tackle a question for the ambiguous case of the sine law. In this question, we have two sides given to us, 15 and 13, side A being 15, side C being 13, and we're also given a non-contained angle of 35 degrees. This is ambiguous because although I have it drawn here, you actually don't know how many triangles you can create. The problem is, with this angle of 35, you could have a nice triangle that looks here, your basic sort of what everybody imagines, but you could very easily change this triangle by swinging this 13 arm in here. Because although we know this angle is 35, we have no idea what this angle is, and we don't really know what this angle here, which would be angle A, is either. So if we swing that back out, you can see that it could be two possible lengths, or maybe it doesn't even work. Maybe I can't even draw a triangle that looks like this. All right, so how do we tackle this problem? Well, we're going to tackle this problem simply by starting with the sine law. So we're going to take sine A, so we're going to look for angle A. So let's see if we can find out what this angle over here is. So sine A over A is equal to sine C over C. All right, so to manipulate that around, we're actually looking for angle A, so A times sine C over C. I fill in my values, so sine A is equal to sine of 35 over 13 times 15. So just a simple application of the sine law. I then find that sine A is equal to 0.6618. That's the ratio times 15. This is a really important part. If this number right here, this 0.6618, if that value is greater than 1, we actually have a situation where no possible triangles can be created. Because of this, we would say that we're done. There's no triangles. You can't make a triangle with a 35, 15, and 13. It just doesn't happen. But because this is less than 1, we can keep going, and we can do the inverse sine to figure out what angle A is. So the inverse sine of 0.6618, and we find that angle A is equal to 41.43 degrees. So that means this angle right here is 41.43. And now we can calculate angle B. Well, angle B, because the triangle theorem tells us that angle B is simply 180 minus A and minus C. I go through the works, 41.3, 43, 35, I subtract them from 180, and I find that angle B up here is actually 103.56 degrees. So, simple as that. That's just basic application of the sine law to find an angle. And two angles, actually. All right, so now we have to do a check for a second triangle. Is it possible to have that sort of skinny triangle over here? So how do I test that out? Well, I go back to my angle of 41.43. Because this is angle A, and that's what sine told me. Sine never gives me a value for an obtuse angle. So to get an obtuse angle, I have to go 180 minus the value that sine tells me. So 180 minus 41.43 gives us an angle of 138.56. This is our other possible angle. It is possible, maybe, that we can say a second triangle with 35, 138.56, and some other value up here for angle B. How do I test that? Well, I take that value and I take my 35 degrees, so I take my two values and I add them together, or I subtract them from 180. If I can subtract them from 180 and get a value that is positive, I'm good to go. So when I subtract these, I actually get an angle of 6.44 degrees. If this turned out to be a negative value, or the sum of these was greater than 180, I have only one triangle. But I actually do have a triangle, and it's got a little tiny skinny angle of 6.44, so it actually works. All right, so here's our two triangles. Here's triangle number 1. Here's triangle number 2. One has some tiny little angles and a big angle. The other one just looks more like a standard triangle. We can label our values. Angle C, 35, 41.44, and 103.56. Our 15 and 13 haven't changed. Over here, 35, 138.56. The sum of these is 180 because they're the opposite of each other, and 6.44, which is that tiny little angle we just found out. The 15 and 13 stay the same, but we end up with a much smaller side for B here as compared to here. Over here, because it's opposite the bigger angle, the biggest angle, we're expecting the bigger value here. And over here, because it's opposite this tiny little 6 degree angle, we'll expect a small value here. So let's do number 1 first. So we attack it with sine law again. So we have to use our B, angle B up here. So side B is what we're looking for. So B over sine B. And I'm just going to use C and C. So c over sine c, I manipulate my equation, so b is equal to sine b times c over sine c, fill in my values, and calculate this out. So I end up with b is equal to sine of 103.56 times 22.6. That's what this ratio works out to. So b, or this side here, is 22.03. I now go to my second triangle. I do the same thing. B over sine b is equal to c over sine c. I manipulate my equation, so b is equal to sine b times c over sine c. All I did was multiply both sides of the equation by sine b. So b is equal to sine of 6.44 times 13 over sine of 35. So sine of 6.44 times 22.66 again. And we end up with side b being 2.54 units. So very big difference between my two sides. One is 22, one is 2.54. I have two triangles. That's the sine law of the ambiguous case of the sine law in a nutshell. And as I've been told to say, live long and math on.